So first of all, I want you to decide if this sequence is arithmetic or geometric. A little bit of review from the other last week. And if so, I want you to find the nth term formula. In other words, I want you to find the explicit definition for the formula. Arithmetic or geometric. And once you figure out which, I want you to write the explicit definition for me. All right, so arithmetic or geometric? Arithmetic, how do you know? They have it goes down by 8 every single time. So we have a common difference, right? We're decreasing, so our common difference is a negative 8. So then how do we find the nth term? Minus a negative 8, good. So minus a negative 8 will be 122. Okay, so that's one way of writing it, isn't it? Okay, and then if you use the book's method that they suggested, you could have said a sub n is 114 plus n minus 1 common differences, and our n was a negative 8. Okay, both get you the same thing. All right, so the next one. Arithmetic, geometric, or neither? Neither. Why, Caleb? So common difference of 3 and 5, so it's not arithmetic. And when we divide 4 by 1, we get 4. And 9 by 4, we don't get 4, right? So it's neither arithmetic nor geometric. Okay? Can anyone figure out what the pattern is for that one, though? Number squared. A sub n is number squared. So it's not arithmetic, it's not geometric. What would we call that? Quadratic. Good. Okay. And anybody notice a pattern here? They go up by 2. So our first differences aren't the same, but our second differences are. And we'll talk about that again in just a moment. Okay. All right. So this is a screenshot from your book. You will not be asked to memorize these. I want to make sure that you can apply formulas using your order of operations and so forth properly, but you won't be asked to memorize these. If I ask you to do any of these for your tests, you will be supplied with them. Make sense? Okay. So there's no sense in memorizing something that a low cost benefit ratio with it. Okay. So what they have done is people have said, hey, is there a formula that I can use to make these things a lot quicker? Okay. Hopefully on an ACT or an SAT, you'll have your graphing calculator. If they ask you to do something like this, you can quickly put these in and not have to work them out. But if we are asked to find the sums of powers of integers, they found out that there is a formula that you can use if you want to add up all the numbers from 1 to n. And it is n times n plus 1 over 2. Okay? Likewise, it's the same thing. You will get the same result if you find your sum of your arithmetic sequence, right? Anybody remember what that formula was? N divided by 2. First plus last. Okay? They're equivalent. They'll get you the same result. Okay? So don't memorize a whole nother formula. But if you like the second one better, then by all means use it. Okay? All right. So if we wanted to get the sum of n squared, you take 1 squared plus 2 squared plus 3 squared plus 4 squared plus whatever, however many numbers there are up to n squared, and that's equal to n times the quantity n plus 1 times the quantity 2n plus 1 all over 6, and so forth. Okay, so I would like you to find this series for me, the sum of, as I goes from 1 to 8, of I cubed, using one of those formulas. Mm-hmm. Yep, exactly. So you have to identify the right formula first, and we're trying to find I cubed, aren't we? So we're using the third formula, and this says to find 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed up to 8 cubed, right? So if we're using this formula, we're going to plug 8 in everywhere we see n. Everyone get 1,296? Awesome. Okay. Example 2 of this nature, we're trying to find the sum as I goes from 1 to 5 of a little bit more. Okay. This time we want 3 times I squared minus 5 times I. Okay. So we have a combined series, right? So we can split it up, and we can say that this is going to be 3 times the sum as I goes from 1 to 5 of I squared minus 5 times the sum as I goes from 1 to 5 of I. We can pull this 3 out in front, the 5 out in front, make them two separate summations. Okay. So now use your I squared or your n squared and your n formulas. Everybody get 90? Questions on this one? wanted I squared, we took our 5 times 6 times 5 times 2 is 10 plus 1 is 11. So 5 times 6 times 11 over 6. Right, or 6 divided by 6 is gone. 5 times 11 is 55 times 3. That was outside. Make it smaller before we make it larger. 6 and 2 cancel. We have 3 times 5 is 15. 15 times that negative 5. Okay, lots of ways you can do these. Then we subtract. Yep, there's a minus sign in between. Okay. Questions on this one? Okay, feeling good? All right. So that was the sum of powers of integers. Okay, someone developed these formulas for us, right? They verified that they actually work, and they will work for every subsequent term. Okay, not just for the first few, but they also work further on down the line. Okay, you do that using something called mathematical induction. Okay, you decide, hey, let's make sure it's true for the first term, and now let's try it for the k plus 1 or the n plus 1 term to make sure it works for that. All right, so next one, we're going to use a model, or use the pictures, the images here, to come up with a sequence based on a pattern. So our table has n for our term number, and then the number of edges are given for the first couple. So our first block, we're thinking about a quilt made of one block. How many seams or how many edges would we have to sew around that block? Well, first term, it's a square, 4 sides, right? So 4 edges. Our second box has some navy blue boxes or blocks added around that yellow block. So how many edges does that one have? 20, because there were 4 to begin with, right? And we added 4 blocks that have 4 sides, right? 4 times 4 is 16. We added 16 to it. We got 20. All right, third one. How many teal blocks or light blue blocks did we add? 8. So 8 times 4 is 32. We already had 20 edges, and we're adding 32 more, so we get a total of 52. Okay. Picture 4, or pattern number 4. How many new blocks did we add? How many reds? 12. 12 times 4 is, so 48 plus 52? 100. Okay. Image 5. How many blocks did we add? 16. Okay. 16 times 4 is, and 64 plus 100 is, okay. We don't have a picture of the 6th block, but how many new squares are we going to be adding? 24. 24 times 4 is 96. 96 plus 164. Okay, something not quite right there. I don't think it was quite that many. So we had added, here we added 4, right? Here we added 2, 3, so 8. Here we added how many blocks? 12. This time we added 16. So how many blocks are we adding the next time? 20. So 20 times 4 is 80. And 80 plus 164 is? 244. Okay? 244. It was 1, 2, 3, 4. Because I wanted you to be able to do it without that last picture. So we extended it one beyond. Yep, there are 5 pictures, but only, and we wanted to find the 6th term. Okay, see if we could extrapolate that. Okay, so far so good, right? Now, is this arithmetic or geometric? It's arithmetic. We have a common difference of the same. So not arithmetic, right? It's quadratic. Good. Because it's not geometric either, is it? 20 divided by 4 is 5, right? But 52 divided by 20 is not 5. Okay, so we know it's not arithmetic and it's not geometric. So differences here are, and how much for this one? Now, second differences. And 16, okay? So we know it wasn't linear or arithmetic. We know it's quadratic. Okay, so what is the general form, the standard form of a quadratic equation? At least what our old books called standard form. Anyway, okay, so it could be n squared, right? A sub n equals n squared. But it could also be, think about the quadratic formula. When we learned the quadratic formula, what did we use for our equation? Mx plus b is linear. Good. So negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Where did those numbers come from? Where did the a, b, and c come from? No. The standard form of a quadratic equation, right? Standard form, what was it? Where did the a come from? The first term, right? Where did the b come from? And where did the c come from? Whatever, okay? So that is our standard form, or at least what our old book called, the Algebra 2 book called the standard form of a quadratic equation, right? Wasn't very helpful to us, was it? When we were trying to graph these things, we like to have it in the form of ax minus h squared plus k, okay? We liked that better than this, but this will be helpful to us. Okay? Everybody remember the standard form of a quadratic equation? Okay, so we know it's going to look something like this, but we don't know what the number in front of n squared is going to be, or the number in front of n, or the constant. Okay? But we can find them. And we do that by starting with our first three terms. Okay? Starting with our first three terms. Our first term, when n is 1, a sub 1 is a times 1 squared plus b times 1 plus c. Or a plus b plus c equals a sub n, which was 4. Okay? Let's let n be 2. Okay? When n is 2, we're going to let us put in 2 everywhere we see n. So a sub n will be, so 4a plus 2b plus c, and that's equal to 20. Okay? And then finally, we're going to let n be 3. So a sub 3, or 52, will be equal to 3 squared times a, 3 times b, and c. 3 variables means 3 equations, right? We have a system of 3 equations with 3 unknowns. One of them was a plus b plus c equals 4. Another one was 4a plus 2b plus C is 20. Sorry, is, 20. And then our third one is 9A plus 3B plus C is 52. Now we have at least 5 different ways that we can solve those equations. Okay? But remember elimination from chapter 8, right? Or chapter 7. Everybody remembers using augmented matrices, right? You all remember how to find the identity, right? Put the identity on and find the identity and work it out, and then multiply the identity times our answers. We also know that we could use our graphing calculator to find the inverse matrix, right? Okay, the inverse of A times the answer. And then we also have Cramer's rule, okay? So we have tons of ways that we can solve this. Make sense? Which one do you want to use? Cramer's rule? Okay. Cramer's rule. Not Cramer's rule? We have to find you have to use 3 matrices, actually 4 matrices, the determinant, right, of the coefficient matrix, then the determinant of the x, and the determinant of the y, and the determinant of the z. Augmented matrix would work too, right? But those of you with a graphing calculator, maybe you want to just use find the identity, or find the inverse, right? If you have a graphing calculator, our first matrix would be 1, 1, 1, 4, 2, 1, and 9, 3, 1. Taken times A, B, C, right? So if we find the inverse of this, and we take that times the 4, 20, 52, we'd have our answer. Okay? And when we do others of these types of problems, do you think they're going to have the same basic pattern here, but maybe a different answer, right? A different 4, 20, and 52 will change, but we'll probably always have a first term, a second term, and a third term. So we'll always have an A plus B plus C is something, 4A plus 2B plus C is something else, and 9A plus 3B plus C is another thing. So once you get this in your calculator, you're probably going to use this most of the time with a different B matrix. Okay, so those of you with a graphing calculator, I suggest you use that. Okay, those of you who don't have a graphing calculator, let's work it out using elimination. Okay, so, and we could use, if anyone wants to see Cramer's rule, I'm happy to do Cramer's rule. Okay, let's use elimination. If we're using elimination, let's take our bottom, our third equation minus our first. So we'll get rid of our C's. Okay, so equation 3 minus 2. 9 minus 4 is 5A. 3B minus B is B. C minus C is gone, and 52 minus 20 is 32. Now let's take equation 1 minus equation 2. A minus 4A is a negative 3A. B minus 2B is a negative B. And 4 minus 20 is negative 16. Does everyone see why I wanted to take equation 1 minus equation 2? The b's go away. Okay? So 5A minus 3A is 2A. And 2A is 16. That means A has to be 8. Okay? Now that we know that A is 8, or did I lose you? Okay? So A is 8. And then we're going to plug it back in, and it doesn't matter which of these two we plug it into. So 5 times 8 plus B is 32. So 32 minus 40 is going to get us a negative 8. And then let's plug them both into the top equation. 8 plus a negative 8 plus what gets me 4? 4. So C is 4. The negative 8 came from, I just plugged it into the top of these two, one of these two equations, doesn't matter which one. So positive, so 5 times 8 is 40, right? And 40 plus b is 32. Subtract 40 from both sides and we get a negative 8. Okay? Why did I do this one? Oh, we wanted to, good question, okay? So if you have this matrix equation, 1, 1, 1, 4, 2, 1, and 9, 3, 1, and we take that times A, B, C, we get our answer, which is 420, 52. Okay? So what we really want is on this side to be the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Everything's 0 except for the main diagonal, which is 1s. Okay? Because if we have that, then identity times ABC will be our answer. It'll give us an A, a B, and a C. Okay? But in order to do that, we need to find the inverse. Okay? So if this is A, if we take that times A inverse, we get our identity. And that means that we have to take this side also times A inverse in order to balance the equation. Whatever you do to the left, you have to do to the right. Okay? Make sense? So those of you who did the graphing calculator, did you get 8, negative 8, and 4? Okay. So our final answer then is A sub n is 8n squared minus 8n plus 4. Feeling good? Questions about this one? That's your final answer. And this one was longer because we had to generate the terms. We gave you a picture and said, hey, what's this going to look like? Okay, let's look at another example. Anyone have any other questions on this one? Okay, let's look at the next one. So now we want to find a model for the sequence 5, 10, 17, 26, 37, 50. First differences are what? 5, 7, 9, 11, 13. All right, so now the second differences are by 2's, aren't they? So we know it's quadratic. Okay. Once we know it's quadratic, we're using the form A sub n is A sum A times n squared plus sum B times n plus C. And we've got to find out what A, B, and C are. Okay. For our first term, we know that we get a 5. When we take A times 1 squared plus B times 1 plus C, we get 5 out. Okay. When we let n be 2, then A times 2 squared plus B times 2 plus C gets us 10. And now when we use our third term, when we let n be 3, A times 3 squared plus B times 3 plus C gets us our third term, 17. Now you could have used the fourth or the fifth or whatever, but these numbers start to get big, don't they? Okay. So again, you have this same matrix. If you're one of the people who are lucky and have a graphing calculator, you've got A stored. Modify B, find A inverse times B, and your answer. Okay, let's use Cramer's rule on this one. Okay, to use Cramer's rule, we need to find our derivative, and then we need to find the derivative with the x's replaced, the derivative with the y's replaced, and the derivative with the z's replaced. But now these aren't x's, y's, and z's now, are they? So we'll replace C Yep. We'll call them A's and B's and C's this time because we're using different variables now. Yep. Yep. So first we'll find the derivative of the coefficient matrix. Okay, coefficient matrix is 1, 1, 1, 4, 2, 1, and 9, 3, 1. Okay, so rewriting our diagonals. And then we're going to get, 1 times 2 times 1, 1 times 1 times 9, and 1 times 4 times 3, negative 18, switching the signs. Okay, so now we've got a negative, and then a 23. So my D is a negative 2. Okay, derivative is negative 2. Okay, now let's do it with the regard to A. With A, we replace the first row with 5, 10, and 17. Keep the second column, first column with 5, 7, 10, and 17. Keep the second and third columns the same. So diagonal down, 10, 17, and 30. Diagonal up, negative 34, negative 15, and negative 10. So diagonal up, we're going to have a negative negative 59, and downward 40, 57, positive 57, so a negative 2. Okay, so for our A, we're taking negative 2 divided by negative 2, so we get 1. Okay, now B's, replacing our middle column by our answers of 5, 10, and 17. Diagonal down, 45, and 4 times 17. So a total of 10, 55, 55, and 68. 123. Upwards, negative 90, negative 17, and negative 20. So negative 220 or 127. All right. Negative 127. So a negative 4. So we take that negative 4 divided by the negative 2, and we get 2. And then finally, derivative with respect with the C's replaced. I'm going to move it down so we don't run into these numbers. Because when I want my dA over D, yep, and dB over D, yep, nope, I didn't. Did it mentally. And then finally, our last one, replacing. 5, 10, and 17 are going in my last column. And then our 1, 4, and 9, and 1, 2, 3. So takes up a lot of space, but doable. All right, so 1, 4, 9, 1, 3, downward diagonal 34, 90, and 60. Upward diagonal 10, 90, negative, and negative 30, and negative, what was it again, 68. So 9, 10, 11, 12, negative 188, and a positive, what was it? So we get a total of negative 4. So negative 4 divided by the negative 2, and we get 2. So n squared plus 2n plus 2. All right, those with the graphing calculators, do the inverse method. Did you get the same thing? Probably faster, right? Okay. Questions on this one? Your button that you're wanting is the x to the negative 1 power. Okay, it's actually not the negative 1 power, it's the inverse button. Okay, it is you take the a inverse times the a inverse is the 3 by 3. Take that, find the inverse, and then take that times your b, which is your 3 by 1. Your 3 by 1 has your answers in it, 5, 10, and 17. Okay. All right, are we feeling good about these, or do we want to see one more? One more? Okay. All right. For those of you who are feeling good about it, here's the assignment. Jot it down quick. You can get started. If you want to see one more, I'm happy to show you. $6.43. Okay. Oh, sorry. All right, last example. Oh, sorry, need more time? I wrote it over here too. I also wrote it on the board. All right, last example. So we have first differences of 4, 6, 8, and 10. Second differences are 2s. So we know it has to be quadratic. Okay. So that means that our first, when n is 1, we will have 1 squared times a plus 1 times b plus c, and that's equal to 0. Okay. N is 2 means 2 squared times a, 2 times b, c equals 4. And now n is 3, so 3 squared times a, 3 times b, c, 10. 3 equations, 3 unknowns. We can stop there. We don't have to make any more. Okay? So what method do you want to use to solve? Graphing calculator? Yep. And the answer to it, if you pulled it into your calculator, is n squared plus n minus 1. Okay. Might have been minus 2. I'll have to check. We'll check it. Oh, I put 10 instead of 18. 0, 4, 10. Okay. So we can work it out real quick. Okay. So graphing calculator to the rescue. All right, so 3 by 3, and we have 1, 1, 1, 4, 2, 1, and 9, 3, 1. Okay, and then we need a new matrix B. And this is a 3 by 1. And it is going to have 0, 4, and 10. Okay, not 11, 10. All right, so now we go and quit, and we want matrix A inverse. So matrix A inverse, not squared. There we go. And we want to take that times matrix B. And I did something wrong in one of my matrices doesn't have it right. A 4 into A or B. Ah, gotcha. So I need to go with matrix A. You're probably right. Let's edit A. 1, 1, 1, 4. My buttons are too close together apparently, or not calibrated properly. All right, so now quit. And then let's do the same thing that we just did before. Entry, and should be -2. Okay. All right, questions on this one? Okay. Uh-huh. Mm-hmm. Absolutely. So let's look. Yep, let me go back and I'll show you what it would look like with linear. It's just an arithmetic sequence, right? Okay. So when we get back to our very first one, we saw this was -8, right? So if we wanted to put this into y equals mx plus b form, yep, so it's like a sub n is equal to mx plus b, kind of, right? So our m is our difference. We actually modified it. So it's just like our arithmetic sequence, okay? Yep, a1 minus the difference, yep. So -8n, we have to minus a minus difference, so we're going to get a 122 when we take away a -8, so plus 122. You're welcome.